All right, so 2.1, Introduction to Chapter 2 on Stability Performance. So I said, there's three main criteria that we'll use for control system performance. The first is stability. It's got to be stable, so that's our first one. We're going to look at that in this chapter. And then next we're going to look at the transient response performance. And then thirdly, we'll look at the steady state response performance. So neither the transient nor steady state performance criteria matter if your system's not stable. So that's you gotta have that. That's basic, but we need to always keep it in mind when we're designing, because you can make things go unstable pretty easily, actually. So it's the most important one. We will now turn to stability considerations, limiting ourselves to LTI, linear time invariant systems, which comprise a lot of systems, a pretty large class of systems that can be approximated as being linear and time invariant. Recall that a system response can be considered to be composed of two parts: the free response, which is due to the initial conditions, right, and the forced response, which is due to the input, the forcing of the system. This terminology will be used throughout the following, so this is to keep that in mind. Those are the two things. That we're going to first look at stability in terms of the free response. And this is the one that we're going to focus on, is the free response stability. So using the concept of the free response, we define the following types of stability for LTI systems. An LTI system is asymptotically stable if the free response approaches zero as time approaches infinity. So you start at some initial condition, you let the system go, evolve in time. If it approaches zero, then we're stable. That's our stable system. Second type of stability we'll define is an LTI system is unstable if the free response grows without bound as time approaches infinity. So that's the blow-up situation where your solution would have an increasing, a positive exponential. So that would be unstable. And then finally, there's a marginal stability case. It's marginally stable if the free response neither decays nor grows, but remains constant or oscillates as time approaches infinity. So that's the case of having, say, an oscillator where if you have say a spring mass, no damper system, and you just let it go, it'll just oscillate back and forth forever. That would be marginally stable. Neither grows nor decays in amplitude. So, stability defined by the forced response. This one is important to keep in mind. Yeah, question?
Does that mean clocks are marginally stable?
So pendulum, if you have a pendulum that has zero losses, then it would be marginally stable. So a pendulum typically has some loss. It's just super tiny, so it'll go back and forth for a very long time without losing its energy. Especially if they're really tall, they'll go back and forth for a really long time. But there's a little bit of air resistance when it goes back and forth, and so it loses a little bit each swing. So I think that electronic clocks supplement the pendulum swing so that it doesn't stop. But just a free pendulum, which are actually really cool. I like pendulums. Pendula? Is that the? Oh, pendulinum. I don't know. Whatever plural for pendulum is. Yeah, they're pretty cool. But they're very, very low damping. So they tend to oscillate for a long time and not stop.
So I'm trying to think of an example. So a clock, because the clock is stable, but the I guess the mechanics of the clock would be marginally stable.
Yeah. So if you're just looking at the pendulum without any active elements in it, that's going to be almost certainly stable. because there are going to be some losses. It'll drag those poles into the left half plane, and you're going to have a decay that'll happen just very slowly. It's very difficult to find examples on Earth of undamped systems because everything's got some friction or something associated with it. There are, like, if you go down to quantum mechanics level, you can get oscillators, harmonic oscillators that have no damping. And if you go to the like planetary motion level, you can get things that are zero damping, like that. But things that are like earthbound tend to have some damping, unless you have a control system. If you have feedback on it, then the closed loop can be marginally stable. I mean, I say relatively easily, essentially. It's much easier to get a marginally stable system that has feedback associated with it. So once we get into this realm, things that have friction in them can still be marginally stable because you have the feedback loop and you're adding energy in. When you keep adding energy into a system, you can make it into a system that is essentially unstable or marginally stable pretty easily. Yeah.
Pendulums or pendula?
Pendula. Okay, cool. Great. So there's another way of defining stability, which I wanted to hit relatively quickly. But an alternate formulation of stability is called bounded input, bounded output, or BIBO stability. And we mentioned this slightly, or just in passing earlier too. This is not the one we'll focus on, but it's good to keep it in our minds. So a system is BIBO stable if every bounded input yields a bounded output. So this is defined not in terms of the free response, but in terms of the forced response, which they're usually very closely related, but there are a few like edge cases where there can be some variation. And then second, a system is BIBO unstable if any bounded input yields an unbounded output. In terms of BIBO stability, marginal stability then means that a system has a bounded response to some inputs and an unbounded response to others, which is technically unstable in terms of BIBO, but you can say it's like marginally stable. It's like a sort of it's not a rigorous definition of, it is still included in the unstable definition, because if any input yields an unbounded output, it's BIBO unstable. So for instance, a second order undamped system, which we were just talking about, to a sinusoidal input at the natural frequency is unbounded, whereas every other input yields a bounded output. So if you put in a sinusoid at the natural frequency, or if you put in any input that has a component at that input continuously, or at that frequency continuously, then you will continue to feed energy into the system at that resonance, and it will continue to increase in amplitude, unbounded. So that's where you start to see there's some subtleties with BIBO stability that are kind of interesting, kind of cool. We aren't going to explore them, but it's good to keep that in mind. Yeah. All right, so that's all I have for that. Any questions on the definition, focusing on these definitions of stability? We're going to make it more specific in the next lecture.